Hello everyone, welcome to lesson 4-8, quadratic functions. As we continue to address the question, how can we model relationships between quantities, we're going to use vocabulary such as quadratic function, and we will define what a quadratic function means. So let's do that now. In the previous lesson, you learned about nonlinear functions. A special type of nonlinear function is a quadratic function. A quadratic function is a function in which the greatest power of the variable is 2. Its graph is U-shaped, opening upward or downward. Complete the graphic organizer by determining if the facts about quadratic functions are true or false. If false, give the true fact. So let's see. A function in which the greatest power of the variable is 2. The greatest power of the variable, exponent, right, is 2. Well, we just said that that's true, right? So let's write true here. Now let's look here. These are all definitions or points that we can make about quadratic function. This is a brain map. The graph is a straight line. No, it's not. These are false. It's a nonlinear function that can be reflected on both the positive and negative side. So this would be false. And because it's false, we were asked to give a fact. The graph is U-shaped. Okay. The graph always opens downward. No, in the definition it says that it opens upward and downward. So again, this one is also false. So we can say the graph can open upward and downward. And the next point, the graph of a quadratic function sometimes opens upward. Well, we just said that, right? So this is true. And these are important facts about quadratic functions. Now let's try a real-world example. Chris kicked a soccer ball straight into the air. The height h in feet of the ball after t seconds is found using the equations. The height equals -16 times t times time squared plus 40 times time plus 2. What is the highest of the ball after what is the height of the ball after 1.5 seconds? So we just have to solve here for h. We're going to replace, we've been given the time, right? 1.5 seconds. We have to replace it here and here. So let's do that. So I first write out the formula they gave us, and now I'm going to replace the variables t's there and there. And now we can solve. So I have h equals -16 times a positive number, but this positive number is squared, so we have to multiply 1.5 times 1.5 into itself. Okay, so I have -16 and 1.5 times 1.5 is 2.25, right? Plus 40, but 40 times 1.5. 40 times 1 is 40, and 40 times a half is 20, so this would be 60 plus 2. And sorry, that's a bad -60.25. And now -16 times 0.25, so I double it and then I have a quarter of it. So I double it and it would be -36. If I double it, it's -32. And if I add a quarter of 16, it's 4. So it's -36 plus 60. Well, I could just say plus 62. I'll just compound those two together. And now it's h equals, what am I missing here? Looks like it's going to be 26. And it's going to be 26 feet because our question, if we look over here, is asking what is the height of the ball after 1.5 seconds. The height is going to be at 26 feet. Okay, and now we come to our first key point, quadratic function. What are they, essentially? A quadratic function can be written in the form of y equals a times x squared plus b times x plus c, where a cannot equal 0. The graph of a quadratic function is called a parabola. The graph opens upward if the coefficient of the variable that is squared is positive. So it will open up upward if the coefficient, the number that we multiply in times the variable, is positive. The coefficient of the variable that is squared. It'll open up downward if it is negative. If it's a negative coefficient. So let's see what we mean by that. Example 1. Graph y equals x squared, right? To graph a quadratic function, make a table of values, plot the ordered pairs, and connect the points with the smooth curve. So essentially, when you have to make a table of values, this is the same as making a linear function, but except now this will be our rule. So we need an input, okay, and we get our output right there when we implement the rule. So we choose -2, -1, 0, 1, and 2. We replace our x, okay, and we solve, and we get our y, and then we get our ordered pairs. And when we graph it, we'll get a nice, smooth, upward opening, as you can see here. Okay, let's see number 2. Okay, with number 2, now our coefficient, which would be 1, don't forget there's a 1 in front of that x, is now negative. Because the coefficient is negative, as mentioned earlier, we're going to have a downward opening curved U-shaped line, or I guess this would be an N. So we choose again our same inputs. We use this rule, negative x to the power of 2 plus 4, to solve for our output, our y, and we get these ordered pairs, and then we graph them. Okay? So here's our example that we can work on together. If you think you understand it, please pause the video now and try it on your own. Pause now. All right, I hope you paused the video. As you can see, I got to jump on my answers already, or I made some progress where I've created my table. I put my input here, my rule, and my output. Okay, I guess I can make one more column where I'll have my ordered pairs, right? My x and y, right? And now I'm ready to input my x's into each one. So here I'll input my -2, my -1, my 0 to replace the x's, my 1, and my 2. And I can solve now. -2 times -2 is positive. Right here. I'm right here, by the way. -2 times -2, because I'm solving for the exponent first, and then I will multiply. -2 times -2 is positive 4. Positive 4 times 6 is 24. So y is 24. Okay, -1 times -1 is 1, and 6 times 1 is 6. And then 0 times 0 is 0, and then 6 times 0 is just simply 0. And then 1 times 1 is 1, and 6 times 1 is 6. And then 2 times 2 is 4, and 6 times 4 is 24. So you can see it's going to be a mirror, right? And now I can set up my order pairs all right here. And here's my list of my order pairs. Notice how we got 0, 0, so you know that that's going to be my epicenter there. And then how can I use increments for my y? I could use increments of possibly 6, maybe. I could say this is my 6, this is 12, this is 18, and this is 24. And I can use increments of just 1, 2. So I have -1, -2, -3, -4. And the other way, I have 1, 2, 3, 4. And now I can graph. So my first one is -2 and 24, which will be right there. -1 and 6, which is right there. 0, 0 is right there. 1 and 6, 1 and 6 is right there. And 2 and 24 all the way up here. And my line is going to look like that. And there we go. It's a positive upward opening. Example 3. Let's read it. The function d equals 4t squared represents the distance in d, right? So that's the distance, the outcome, in feet that a race car will travel over t seconds with a constant acceleration of 8 feet per second. The graph the function then use the graph to find how much time it will take for the race car to travel 200 feet. Okay, so here we have our times from 0 seconds, okay, our time all the way up to 6 seconds, correct? Okay, they wanted us to use T for seconds, our time. We replace them, we get our output, which is our Y, and we have our order of pairs, and then we graph it. And there we go, we graph it. So to locate 200 on the vertical axis, we go right here. All right, there it is. Okay, we locate 200. Move over to the graph and locate the corresponding value for that time. So when we do that and we find it, we drop straight down and we see that it would take 7 seconds to travel a distance of 200 feet. So these types of functions can help us predict distance over time, right? So the car will travel 200 feet after about 7 seconds. Let's see number 4. Okay, same idea, different numbers. The function h equals 0.66 times d squared represents the distance, again, in miles you can see from a height of h feet. Okay, graph this function, then use the graph to estimate how far you could see from a hot air balloon 1,000 feet in the air. So 1,000 feet, how far can we see? So what we're going to do is we take our distance, so 0, 10, 20, 30, 25, and so on, increasing by 5. And our distance, okay, is measured in miles. So 10 miles, 20 miles, 30 miles. This is how far, okay, we can see. And based on the height, okay. So we input and replace all our x's again. We multiply and we get our order of pairs. We have our height and we have our distance. So if we go all the way up to, okay, 1,000 feet in height with our air balloon, we're able to see a distance of up to 40 miles. See that? So again, at a height of 1,000 feet, you can see approximately 39 miles. Okay, yeah, 39 miles. That looks more correct. And finally, for our last example, you can try it on your own. Here it is. Just follow the steps from example 3 and 4. The outdoor observation deck of the Space Needle in Seattle. Okay, so if you step out into the balcony and you look out, this is like Seattle CN Tower. Washington, it is 520 feet above ground level. Okay, that's how high it is above ground level. Use the graph to estimate how far you can see from the observation deck. Okay, so it's 520 feet above ground, so 500 is right there here, and 20 would be about, I'm just going to zoom in. Okay, so it's at 520 feet. We go 400, each one is 100, 100, 200, 300, 400, 520. So 20 would be about 1/5 of the way up. And when we go straight across to about there, we can see in miles approximately 28 miles, I would say. Okay? Because if this is 20, this must be 25. And right here, about so would be about 28. So that would be my observation based on the graph. So we can say about 28 miles. Okay, here is our guided practice. Again, take a couple of seconds to take a look through the practice. Make sure that you feel comfortable with what you're being asked to do. And if you're not sure on what to do, go back to the examples or bring your questions to class. See you in class, everyone.